Right, so this is about this is for physics level 2 NCEA mechanics. NCEA level 2 physics mechanics motion questions. This is from No Brain Too Small. So today I'm going to talk about how to apply these kinematic equations into different questions of different scenarios. Alright, so this question first. I wrote these kinematic equations here, so be good for us to use. So for this question, Alex and Joe have decided to take a road trip. They start from rest on a straight road and accelerate at 4.2 meter per second. So I'm reading this sentence here. What can we know from this? I set from rest. What does this mean? This means that the initial velocity is 0 per second, correct? And accelerated 4.2 meters per second, which means the acceleration here is 4.2 meters per second. So show their velocity after 0.6 seconds is 2.5 meters per second. So in A, they've given us the time, this is the t, and show the velocity after 0.6 seconds, which means we're looking for VF, right? So now we see what we have. We have a VI, we have a VF, no, we have a T, we have an A. So to do these kinematic questions, we must have 3 of those. We have VI, VF, A, T, and D. We always need 3 out of 5 to calculate the other 2 or the one that we're looking for. But most of the questions we just have 3 of those, and we're looking for the other or one of the other 2. So now in this case we have a VI. We know what VI is. It's 0 because it starts from rest. We know what the acceleration is. They told us. And we know the T as well. They told us that as well. So we're looking for VF. So now we're doing is looking for the kinematic equation, which has all A, VI, T, and VF. Okay? We're looking for the one equation that has all 4 of these. So because we have 3 of those, then we can calculate what VF is, because we just do substitution, and we can easily get what VF is, right? So in this case, we don't have D, so any equations with D eliminated. So right, this one has D, no. This one has D, no. D, there's a D here, no, because we don't have D. And we don't need to calculate D as well. So we only got this. That's very easy, right? We know we're calculating VF. So VF equals to VI. That's VI is 0. And AT, what is A? 4.2. T times 0.6. So that will equal to I think that will equal to, right, let me calculate this, 2.52 meter per second. Right. So D, okay. While travelling at 50 kilometers per hour, Joe sees a pothole in the road 50 meters ahead. She must reduce her speed from 50 kilometers per hour to 20 kilometers per hour to avoid damaging the car. If the time needed for safe braking from 50 kilometers per hour to 20 kilometers per hour is 2.3 seconds, show by calculation whether there is enough time to complete braking before reaching the pothole. You should start by showing that 50 kilometers per hour equals to 13.89 meters per second. So, they told us that we should start by showing 50 kilometers per hour equals to 13.89 meters per second. So that we should do that, right? So 50 kilometers per hour. I think many of you have learned this in math, that is 50 km divided by an hour. So that's just 50 kilometer divided by 1 hour. And what does 1 kilometer equal to? Like, how many meters does 1 kilometer equal to? That's 1,000 meters. Well, K means 1,000. An hour to seconds, right? We're doing the unit transformation. So an hour equals to 3,600 seconds. Well, an hour equals to 60 minutes, and the minute equals to 60 seconds. So 3,600. That's right. And that will equal to 50,000 meters divided by 3,600 seconds. So that will equal to, well, that must equal to 13.89 meters per second, right? So units here is actually a value, right? You can change units by transforming its value to another unit, because there's a value, well, there's a proportion between the different units. Well, the units are for the same values. Well, right. So go back to the question. If the time needed for safe braking from 50 kilometers per hour to 20 kilometers per hour is 2.3 seconds, whether there is show by calculation whether there is enough time to complete braking before reaching the pothole. So we're calculating the time, right? Looking for the time. That's what we're looking for. And we have the VI. What is the VI? 50 kilometers per hour. Well, that's 13.89 meters per second. That's VI. And that's our VF, because that's our VF, because we're looking for how much time it takes to for the speed to decrease from VI to VF, from 13.89 to VF. So the VF here is 20 kilometers per hour. Do know that there are different units, so we have to change 20 kilometers per hour to meters per second as well. So we will be using the same method. So 20 kilometers per hour. Well, you can do it yourself, but I'm just going to divide this by 3.6. If you, well, that's 5.56 meters per second. Right? So, well, if you do it like this way, you get the same thing. So actually, I'm just gonna, it's like 1 kilometer per hour equals to 3 point, wait, sorry, no, that's not the case. 1 meter per second equal to 3.6 kilometer per hour. So now we got this VF. This is our VF. We got a VF. Looking for the time, and we're going to use this time to compare with 2.3 and see if the time needed is safe for the car to brake. So VI, VF, and we have what? And we have a D. Alright, we have a D. Yep, we have a D. Now we can see what we have, okay? We have VI, 13.89. VF, what is that? 5.56. A, we don't know, so which means we don't need it. D, yes, we do have it. We have 15 meters. 15 meters is it's in its SI units, so we don't have to change the units. And we have a time. No, we don't. And we're looking for the time. That's what we're looking for. Remember, I said that when you have 3 of those, then you can calculate all the other 2. Right? And now we're looking for the time. So we can just ignore A. So go back to the kinematic equations. We don't need A. This one. There's A. No. A. No. A. No. Okay. So now we're going to use this one. We're going to substitute all the values we have in this case. And we're going to calculate what the time is. Right? So the distance is 15. VI 13.89 plus that will be 5.56 divided by 2 times t. Well, the t is what we're looking for. So now what do we have? We have this 15 equals to 13.89 plus 5.56. So I'm going to use the calculator. I can't do it. Divided by 2. So that is 9.725 t. So t equals to what? 15 over 9.725. So 15 divided by 9.725. So t is 1.54, which means that, and this is smaller than 2.3, so it is, yeah, there is enough time. The answer will be enough time. Just don't write it so briefly, so you're gonna, yeah. Actually, I'm not gonna write that. Okay. Next question. Nicole is playing for her school, for her school hockey team. During the game, she passes the ball to her teammate Josie, who is some distance away. To do this, she has to raise the ball. Let me just move this. To do this, she has to raise the ball high enough to give it flight and low enough to keep it safe. She hits the ball with a velocity of 22 meters per second and an angle of 30 degrees. Alright. Show that the initial velocity of the ball is 11 meters per second. So what do you do here? We look at this diagram. Okay. Hits the ball with a 20 meters with a velocity of 20 meters per second and an angle of 30 degrees. So which means 30 degrees and velocity of 22 meters per second. Right? That's the velocity of the ball. Velocity of 22 meters per second at an angle of 30. So we're looking for the initial vertical velocity here. So what we're going to do is, right, so this is a triangle technically, so we're going to use SOHCAHTOA, okay, trigonometry. 30 degrees here, 22 meters per second, and vertical velocity, we're looking for this one. So what is that? That's opposite, that's the adjacent, and that's hypotenuse. So we have opposite and we have hypotenuse, which means we're going to use sine. So sine 30 degrees equals to, we can call this V vertical, actually, over 22. And sine 30 degrees equal to, I think it's half. You can check it for me. I think it's half. Yeah, it is half. So 0.5 equals to v vert over 22. And 0.5, so v vert equals to 0.5 times 22, which is 11. Okay? Done. Describe and explain the motion of the ball. You should refer to any forces acting on it as it moves through the air. You may include a diagram to support your explanation. So that's explanation. So we're going to say is the ball starts with a velocity of 20 meters per second, and its velocity decreases till it reaches the top of the path, and then decreases due to the due to the acceleration of due to gravity. So then it decreases the motion of the ball. I see. So you say, what you're going to say is, you're going to say it starts with a vertical velocity of 11 meters per second, and then it decreases. Wait, no. Yeah, it does decrease. So it decreases till it reaches the path of the top of the path, and then the vertical velocity and the ball starts going downward, and then the velocity when it touches the ground again is the same. The vertical velocity when it touches the ground is the same as the vertical velocity at the start, but opposite in direction. That was a horrible explanation, but I hope it helps. You can search you can use a SciPad, they have it there. Okay. Josie was 44 meters away from Nicole when Nicole passed the ball to Josie in parts A and B. Will the ball reach Josie before it bounces? Justify your answer using appropriate calculations. We have this projectile motion thing, right? And this is 44. Vertical velocity is 11 meters per second, and it ends with vertical velocity of minus 11 meters per second, which is 11 meters per second downwards. So which means we have A here, right? It decreases. Well, it has an acceleration of minus 9.8 because, well, we start with the positive, which is upward speed, and and it keeps decreasing due to the acceleration due to gravity. So that's minus 9.8 meters per second, correct? So now what we're going to do is we can calculate t, because the time for the ball to fly for all depends on the vertical velocity, okay? We can't just say that it takes how much time by dividing 19.05 by divide 44 by 19.05, because that's how it works, right? Because the ball may just fall on the ground and stop moving due to its vertical velocity, due to it falls on the ground because it can't move anymore because it's just on the ground, okay? So we can calculate what the time is in this case. So VF is minus 11 equals to 11 plus minus 9.8 times t. So that will be minus 22 equals to minus 28 t. So t equals to 2.24 s. So now we have t, right? And now we're going to see that if with this velocity, horizontal velocity, and within this period of time, we're going to times this by 2.24 and see if this is bigger or smaller than 44 meters per second. Okay, so 19.65 times 2.24. So that's 42, that, okay? So D equals VT. 42.672, so that's the meters. That's the distance. Because when the ball falls on the ground, it falls on the ground after 2.24 seconds. But the horizontal distance within this 2.24 seconds is only 42.672 meters. It's smaller than 44 meters, so it cannot reach Josie. Okay? It cannot reach Josie. So for this one, calculate the horizontal velocity of the balloon. Show that the initial velocity of the water... Oh no, sorry, just this one. Okay. Horizontal distance of 21. The water balloon is in the air for 2.8 seconds. Okay? 2.8 seconds. Horizontal velocity, what was that? Okay. We have a distance. Well, horizontal distance. In the air for 2.8 seconds, that's the time. Well, that's going to work for the vertical and the horizontal velocity. Okay, well, the horizontal velocity of balloon, well, okay. V equals D over T. 21 over 2.8. What does that equal to? 21 over 2.8, so that's 7.5 meters per second. Okay, show that the initial velocity of the water balloon is 15.6 meters per second. What should I do? What should I do? Is there an angle? Ah, I see. So that's a hard one. Okay, show that the initial velocity of the water balloon is 15.6 meters per second. So if we know what this angle is, we can use SOHCAHTOA, right? But we don't know what this angle is. So what we're going to do is we have this horizontal velocity, correct? And to calculate what the initial velocity of the water balloon is, we can try to calculate the vertical velocity. Right, probably that won't work. Oh no, I don't think it works. Well, let's try. So the water balloon is in the air for 2.8 seconds, okay? Which means from this point to this point, 2.8 seconds. And from this point to the top of the path only takes 1.4 seconds because it's, half and half. Which means 1.4 seconds. And if we just look at the vertical velocity here, when it's at the top of the path, it has a velocity of 0, right? That's by the way, that's vertical. Has to be 0. VI, we all know. A, as always, as it's a vertical velocity minus 9.8 meters per second. Okay. Do we know more about this? We know time. Right, we know time is 1.4 because we're just looking at this section here. Okay. What do we have? Right, I'm going to take this with me. Alright. Bye-bye, VF. Right. Done. Okay. We have a VF, we have a VI, we have A, we have a T. Okay, we have 3 of those, which means we can get the other ones. And we have VF, VI, A, and T, so we don't want what? We don't want D. So the ones with D, bye. So VF equals VI plus AT. VF is what? 0. VI is what? We don't know. So VI plus minus 0.8 times T, 1.4. Okay? So, which means 0 equals to VI minus 13.72. So, VI is 13.72 meters per second. Okay? What we can do here is, I was just wondering if this is going to work, because we can try to use Pythagoras. Let me try. Yep. That equals to 15.63 meters per second, which is 15.6. So it works, right? So I see why they don't give you the angle, because if they do give the angle, which means you can just know what it is. But if they don't give you the angle, but they give you the time, right? You can calculate the vertical velocity, because you know what the VF is 0. You know what the time is. You know what the acceleration is. So you're going to calculate what the vertical one is, and you know what the horizontal one is. And the initial velocity is always, right, is the vertical plus horizontal. Yeah, that's a difficult one. Well, yeah. So C, if the same water balloon was launched at the same initial velocity on planet X, where the acceleration due to gravity was 3.7 meters per second, would the water balloon go the same horizontal distance? Clearly explain your answer. So you must know the concept that acceleration due to gravity is downwards. Okay? Right? It's downwards. Wait, actually, no. No, actually. It will affects the horizontal distance, because you know a lower a lower acceleration, which means we have to change the values. Wait, just mark this. So we're going to change the values here. This case, which means this is 3.7. So this value will be smaller. And this will also be smaller, right? Yeah, it will be smaller. Because it's 3.7. Well, minus 3.7 is smaller than minus 9.8. Well, it's bigger than minus 9.8. So when it's positive, it's smaller, right? Okay. When it's smaller, which means wait, no, the balloon is in the air for 2.8 seconds. Same initial velocity, okay? Which means we have the same initial velocity. Right, we have the same initial velocity. So it's still at 15.63. And the initial velocity is still 15.72. But the time cannot be the same. Because we said, sorry, I was saying the wrong thing before. So launch at the same initial velocity. So VI is going to be the same. And the A is going to change to 3.7, which means the time is going to change. It can't be 1.4. Which means the balloon is in the air for 2.8 seconds. Will change. It'll become like something like I don't know. Well, it has to be bigger than this, because 13.72 divided by 3.7 is going to be bigger than 1.4. So that number doubles, and that's going to be bigger than 2.8. And because of a longer time, and we set the same initial velocity, which means we're going to have the same horizontal velocity, because d equals vt, and longer time, bigger velocity. No, sorry, longer time, same velocity. This is the same. This increases, which means the distance increases. So it will not go into the same horizontal distance, and that is very clearly explained. Back on Earth, Jamie wants to catch a water balloon. He stands 12.5 meters from the launch position, and his hands are 1.1 meters above the top of the launcher. Okay. Launch at an angle of 35 to the horizontal. Okay. Determine if the water balloon will arrive at the right position for Jimmy to catch it. .5 from the launch position, and his ends 1.5. So we can draw a little graph here. By first showing the vertical component of the velocity is 7 meters per second. Okay, so what we're going to do is, got a balloon, 35 degrees, horizontal is 10, vertical is what? So that's what? That's going to be tan. 10 vertical over 10. So tan 35. Tan 35 times 10. Seven. Okay, so determine if the water balloon will arrive at the right position for Jimmy to catch it. So let's see. Okay. Determine if the water balloon will arrive at the right position for Jimmy to catch it. So first let's wait, hold on. 0.1 meters above the top of the launcher. Okay. I see. So I will explain that later. Right, now we'll look at D. Okay. So 21 meters. And we have a horizontal component of the velocity is 10, which means the time it takes from the start to 12.5 meters. No, sorry, that 21 was useless. Okay. 12.5, that's the distance, horizontal distance. Okay, and horizontal velocity is 10, which means it takes, time equals to d over v, sorry. So 12.5 over 10 is 1.25 meters. Oh no, 1.25 seconds, sorry. So which means 1.25 seconds. So in this case, 1.25 seconds. So that means we only have 1.25 seconds for the ball to land, to be at the position where it is above the top of the launcher for 1.5 meters. So 1.25 seconds. So now we have a T, and we have we just calculated the component, vertical component is 7, so we have a VI. And we have A, of course, minus 9.8, and we have a, and we want to have, well, we have VI, T, and A, so we want V, and we want D, because we want to show that it'll arrive at the right position, the right vertical, vertical distance. So the vertical distance has to be smaller than 1 point, but it has to be the same, well, like approximately the same as 1.1 meters, because that's when Jimmy has its hands at the right position. So what's the one that with D that has D, V, I, A, and T? D, V, I, A, and T. That's the one. This one, right? Okay, because we don't need anyone with VF, because we don't even know what VF is. So no. We don't even know what VF is, and it's kind of impossible. Well, it is very difficult to calculate it. It's not impossible, but it is very difficult. So D, well, it's not difficult because we already know what VI, A, and T is, so it's not difficult at all. It's hard to think about what time is, because we have the horizontal velocity and the horizontal distance, so we know that it has to be 1.25 seconds where it lands in the right position. Okay, but we have to show that it's in the exact position, because if after 1.25 seconds where it's at 12.5 meters and it's not 1.5 meters above the top of the launcher, then it is not at the right position. So we want to show that it's the right position. We're going to determine if it's like much higher or much lower than 1.1. It's wrong. Okay, substitute the values. This one, VI is 7, T is what? 1.25 plus half minus 9.8. The T is 1.25 squared. So 1.25 times 7 is 8.75. Then plus half times minus 9.8 times 1.25 squared. That's that whole thing. Equal to hold on. $7.65625. So sorry, that's a minus 7.65, and that just equals to 1.1, right? Which means it is in the right position. Do remember that when you're looking for the time, if you have horizontal velocity and the horizontal distance, because the horizontal speed is constant, so we didn't have to worry about the acceleration of the horizontal one. Okay, when it has horizontal distance and horizontal velocity, that's what we're looking for, because if they want you to calculate it, that's how you're gonna get the time, because you don't even know what the vertical velocity is, so you can't get the time. You only have like 2. You only have VI and A, so you can't get the time. So when you have horizontal velocity and the horizontal distance, you get the time. And do remember that the time for the horizontal velocity, for the time that takes, horizontal distance divided by the horizontal velocity. Yeah, that's the time. That time is the same. Is the same time as the time the vertical velocity. That's the same time for vertical velocity and other stuff. That's the same thing. Okay, just remember that. Okay, that's it for today. I think the ones after are just the same thing.